The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are doing good and regular with your classes. Of course, last week we were not able to upload few classes because of our sports day. So, the other classes I think you would have been seeing it regularly. So, I want you to continue that. Do not miss the classes. Similarly, continue with the notes that you are writing. Don't wait for somebody to push you to do the work, because it is our own responsibility to make sure that we do our work perfectly. So, and there is a HSS Live website also for you. As I have told you earlier, with related to the topic, you look at the questions and the notes so that you make yourself thorough with the topics that are being taken. Right, children? So, with the third chapter, we are into the last part of this chapter, where we are going to see about the periodic trends along the periodic table. Last class we were learning about atomic size, ionic size and electronegativity, electron gain enthalpy, something about screening effect, where the electrons does not allow the nucleus charge, effective nuclear charge to fall on the outermost electrons. So, I think you all remember those things, right? So, this class we are going to see something about valency and oxidation state. Right from our 10th standard we were behind this oxidation state, and we were also having confusion what are this oxidation state referred to. We have been given the name oxidation state for the common term valency. We know valence electrons, this we have been learning right from our 8th, 9th standard. Valence electrons are the number of electrons present in the outermost shell. So, when we say a valency or an oxidation state, it completely depends on the electronic configuration of an element. The electronic configuration of the element will define the valency of the element, or I would say the oxidation state of the element. It is nothing but the number of electrons in the outermost shell, or 8 minus the number of electrons in the outermost shell. Because we know in a periodic table we have primarily 4 blocks S, P, D and F, where the S and P are called as the representative elements, D block elements are called the transition elements and F block are called the inner transition elements. Now, why I am saying all this? Because we know the periodic trend, like our atomic radius, ionic radius, whatever we take, it depends on the block of the element, the group, whether it is down the group or across the period. So, here oxidation state was the chemical name given to the term valency. Now, let us see how an oxidation state can be determined when a compound is formed. Now, you have here two familiar compound, one is OF2, the other one is Na2O. Here OF, both are P block elements. There sodium, oxygen, where my sodium is an S block element and oxygen is a P block element. Now, let us consider the first example, OF2. Now, what happens here? We know the electronic configuration of oxygen is 2s2, 2p4, outermost 1s2, 2s2, 2p4. Total it is atomic number 8. So, it needs 2 more electrons to become stable. My fluorine has got an outermost configuration 2s2 to p5, where it needs 1 electron to become stable. So here oxygen needs 2 electrons, fluorine needs 1 electron. So what happens here? 1 oxygen combines with 2 fluorine atoms, thereby it forms a compound OF2. Oxygen needs 2 electrons, which is given by 2 fluorine atoms, each fluorine atom giving 1 electron to oxygen. But here, how do I calculate my oxidation state? Which one I will consider as my anion or cation? Because we know any element that loses electron becomes a cation, and any element which gains or accepts electron becomes an anion. But on what basis, on what respect that I can calculate the oxidation state? See, we do it with the comparison of electronegativity. If I see my electronegativity of these 2 elements, fluorine and oxygen, definitely we know the electronegativity, it increases across the period, and fluorine is the most electronegative element in the periodic table. So here fluorine electronegativity is more than oxygen, so fluorine will bear a negative charge. So fluorine will have -1. So fluorine, 2 fluorine atoms sharing 2 electrons with oxygen, so it will be -1. So definitely oxygen, because of this 2 fluorine atom, will take a +2 oxidation state. So this is what is in regard with OF2. Now what happens here with Na2O? The case is entirely different. Sodium is an S block element, and we know alkali metals or alkaline earth metals, they lose electrons because they are electropositive elements and they are cations and they are metals. So here oxygen needs 2 electrons, sodium it is 3s1, so 2 sodium atoms combined with 1 oxygen atom, sodium being more electropositive loses these 1 electron, so each sodium atom, so 2 electrons, so becomes sodium with +1 oxidation state. Oxygen accepting those 2 electrons will have a -2 oxidation state. So this is how we calculate the oxidation state of the element. I hope you are able to understand, children. Similarly, we will be given compounds to calculate the oxidation state. Normally we do with the zigzag formula. We used to cross multiply and we calculate the oxidation state. You can apply the same thing also with the electronic configuration. Now we will see how this trend has affected the anomalous behavior in the periodic table. See, we were seeing about the oxidation state in your textbook. You have in table 3.9, if you see, you have been given a table with a comparison of oxidation state, and you can see here the first group, second group, third group, how do they form their hydrides and oxides. So this will help you to find out the oxidation state as well. I think it's page number 90, children. Okay. So now we are getting into the most important topic of this chapter. This word you will be hearing it in a very common way now in the forthcoming lessons and all. It's called the anomalous behavior. Anomalous means something exception, exceptional behavior, some different type of behavior. Now what is exactly happening? Let us see. If you see the second period in your periodic table, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. First group, second group, 13, 14, 15, 16, 17. I have not included the noble gas group here. If you see the third period, we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. So these all they belong to the first group. This is my second group, 13th group, 14, 15, 16, 17. This is my S block and this is my P block. This is what we know. You can just cross check with your periodic table given in your textbook. Anomalous behavior. Now here lithium and beryllium. My first and second group element, that is lithium and beryllium, shows an exceptional behavior, a different behavior from the other elements of the same group. Lithium has to have a behavior just like what sodium and potassium are having. Similarly, beryllium should behave in such a way how the two group elements should behave, because this is my first group, this is my second group. But lithium being an alkali metal, beryllium being an alkaline earth metal, has to form ionic compounds. They are supposed to form ionic compounds. But what happens? They do not form ionic compounds. Instead, they try to form covalent compounds. So, I repeat, lithium, beryllium supposed to form ionic compounds just like our alkali metals and alkaline earth metals. Instead, they try to form covalent compounds. So, what scientists were observing was that lithium was not showing a direct relationship with respect to sodium. Instead, it was showing all the characteristics of magnesium. Lithium, instead of behaving like an alkali metal, it was behaving more similar to that of magnesium. Similarly, beryllium, an alkaline earth metal, instead of showing a direct relationship like magnesium, it was showing a diagonal relation to aluminium. So, lithium with magnesium and beryllium with aluminium. So, the properties or the behavior of these elements were diagonally the same. So, that type of relationship we call it as diagonal relationship. The most important term in this anomalous behavior. Why anomalous behavior? What is anomalous behavior? The property of the first member of my second period, the lithium and beryllium, showing diagonal relationship with magnesium and aluminium of the subsequent period. Such a relationship we call it as a diagonal relationship. What is the reason? What could be the factors that are responsible for this diagonal relationship? The first and foremost is the small size of those elements. Those elements having very small size compared to the other elements in the periodic table. They have a large charge by radius ratio. The charge by radius ratio was very high. If you can see here, they have given in page number 90 the metallic radius ratio and ionic radius ratio of lithium 152, which is similar to that of magnesium 160. Right. So, these are the factors that are responsible for the diagonal relationship. Next one is high electronegativity. They are supposed to have a very low electronegativity, but they possess a very high electronegativity, which make them different from the other elements in the periodic table. Next, the first member has got only 4 valence orbitals. We know lithium atomic number 3. So, it is 1s2, 2s1. Beryllium, if you see, it is 1s2, 2s2. Only 4 valence orbitals are present. Similarly, for boron, if you see 1s2, 2s2, 2p1. So, what happens? Maximum covalency can be only 4. But the second members here will have more than 4, that is they can expand their orbitals, their valency can be more than 4. That is the reason that they show a diagonal relationship. Other members can expand. The first member of the p block element, if you see here, boron, carbon, nitrogen, they all are having the ability to form p-pi multiple bond. P-pi, if I see, they can combine with the same element of their own group and form triple bond. Nitrogen N2, if I say N triple bond N. So, that is called as p-pi bonding, and also with the other members of the periodic table. So, these are the main reasons which is causing the diagonal relationship for those elements of the second period, which is mainly with lithium and beryllium. That is why we say the S block elements try to behave more like a P block element. And we know the metallic character actually changes to become a non-metallic character. So, anomalous behavior, if it is asked, you will give those main reasons. These are the most important first 4 are the most important reasons that are causing the diagonal relationship. Right. Now, we will just get back into the periodic trends and how does it affect the chemical reactivity. Come to the last part of this chapter, periodic trends and chemical reactivity. Now how does this periodic change, that is change in, we have been learning change in atomic radii, change in ionic radius, change in ionization enthalpy, electron gain enthalpy, electronegativity and also oxidation state. How does these changes will tend to the chemical reactivity of an element? See, we know children, as the atomic number increases down the group, the atomic size also increases, the ionic size also increases, but that is happening down the group. What is the trend when it goes across the period? When it is going across the period, we know the number of shells actually it remains the same. The number of shells actually remains the same, but the electrons get added in the same shell. So as the number of electrons get added in the same shell, the effective nuclear charge becomes more. So the nucleus tend to pull the electrons in the outermost shell and it actually shrinks. So that's why we say atomic radii or ionic radii decreases down the group, right? But when you come for ionization energy, now what is ionization energy? The energy required to remove the loosely bounded electron from the outermost shell. So if my electron is far away from the nucleus, it is easy to remove the electron. If it is closer to the nucleus, I know definitely effective nuclear charge is more, so I need to put more energy to remove the electron. That's why we say as the atomic radii increases down the group, ionization energy decreases down the group. But what happens across the period? Atomic radii actually decreases. So when it decreases, the electrons are closer to the nucleus, so the energy required to remove the electron from the outermost shell is more. That's why we say ionization energy increases across the period. So now we will see the physical and chemical properties are directly responsible by the electronic configuration of the element. Atomic radii, ionic radii increase down the group and decrease across the period. What happens to ionization enthalpy, electron gain enthalpy? Both decrease down the group and increase across the period. Now the high chemical reactivity will be at the two extreme corners of the periodic table. My left extreme and the right extreme, it will be more, the chemical reactivity will be more, and it will be lowest at the center of the periodic table, because we know at the left there are loss of electrons by the alkali and the alkaline earth metals. When they lose electrons, they become a cation, and at the right extreme we have the elements which tend to gain the electrons to become a noble gas, and therefore they become an anion by accepting electrons. So what is happening to my metallic character? The metallic character actually, from my left side, if I say they are more metallic when you go down the group, but when you go across the period, the metallic character tend to decrease, and more when it reaches the p block elements, it becomes more non-metallic. And we know in p block elements we have metals, we have non-metals, we have others like metals, semiconductors also are present, insulators are also present. So it's a combination of all the varieties of compounds in my p block elements. These are the general trends when we study about S and p block elements. But if you see children, transition metals, we have this 3D, 4D and 5D series. Around 38 elements are present in my D block elements, which are called transition metals. But we know metals of transition series, they have luster property, they are good conductors of heat and electricity. We also know they show variable oxidation state, they have catalytic property. But what is their trend towards this atomic and ionic radius? The radius are not that differed as compared to that of S and P block elements. The change in the atomic and ionic radii is much smaller when compared to the representative elements in the periodic table. Just like when you see inner transition elements like our lanthanoids and actinoids, their change in the atomic and ionic radii is much smaller when compared to the transition elements. This reason is because of their lanthanoid contraction. We know what is lanthanoid contraction. The screening which is happening in the representative elements is not that effective in the case of D block elements within the same subshell. It is still worse when you come to my lanthanoid series. So the shielding effect is very poor as compared to that of our representative elements. So these are the reasons that make the transition and inner transition series not that effective as compared to S and P block. But also we know that there are noble gas elements which are in the periodic table, which is present at the extreme right end of the periodic table. Now those elements are completely inert. They are chemically inert is because they have their orbitals or shells completely filled. That's why they do not take part in the chemical reaction. So as of this lesson is concerned, we are studying about the periodic properties of the elements in the periodic table. So always remember about atomic radii, ionic radii, ionization energy, electron gain enthalpy, electronegativity. These 5 factors are very important about the change that is happening across the period and down the group, because you may be given a graph with respect to change down the group or across the period like elements and also their atomic radii. So you should be able to relate the graph and understand and explain what has been happening. If the curve is like steep down, then you should be writing that it decreases down the group. Or if it is going higher, you should write it increases across the period. So you should understand the concept related with the elements, because atomic radii, ionization energy are vice versa. It increases, this decreases. If atomic radii decreases, ionization energy increases. So children, this is a very small chapter and you have completely theory in this. I will try to give some important questions from this chapter. Also, you make sure that when you complete this chapter, you take your HSS live link, see all the notes which are important, go to the repeated questions which have been asked, you have solved question answers, then you can check your previous question papers. If you still have any doubt in this chapter, please do not hesitate to ask me so that we can clarify your doubts. With this, the 3rd chapter gets over. The next chapter is completely related to bonding. So if you have your textbook, just go through the text and make sure that you become fresh when you attend the next class. Okay. Until then, stay home, stay safe, take care children, bye.